In this video, we're going to look at how to draw the electron dot structures for organic molecules. So organic molecules are molecules that contain carbon atoms, and those are covalently bonded to other non-metal atoms. Organic molecules are very important. They're essential for life, and therefore we want to be sure we can understand their dot structures, shapes, and polarity. Most organic molecules have more than one central atom, so they can be somewhat small, but they can be also very, very large molecules, and they generally have more than one central atom. However, even though these molecules may have more than one central atom, we can still apply the same rules for drawing electron dot structures that we've previously learned to organic molecules. So let's try a couple. Let's try C2H6 and C3H8. So if you would, pause the video and see if you can draw the dot structures for these two, and then we'll work through them together.
So let's look at the dot structure for these two molecules. First, let's count up our total valence electrons. We know that carbon has 4 valence electrons, and we have 2 carbons. And hydrogen has 1 valence, so we have 6 hydrogens. So 8 plus 6, we have 14 valence electrons in this first molecule. So how do we arrange the atoms in our dot structure? Well, one way we could potentially put a carbon. We've got 2 carbons, and then we could put 1, 2, 3, 4, 5. Maybe all 6 of our hydrogens are bonded to that carbon as well. If we look at that, though, right away, hopefully we can see that this carbon has more than an octet. Since carbon's in period 2, it's not allowed to have anything more than 8 electrons around it, and this one has 2, 4, 6, 8, 10, 12, 14. So of course, that cannot be our dot structure, so we have to try something else. So we know that organic molecules generally have more than one central atom. So let's put our 2 carbons down and put 3 hydrogens around that first carbon. If we put 3 hydrogens, that gives us 2, 4, 6, 8 electrons around our first carbon, giving it an octet. The second carbon can also get 3 hydrogens, since we have a total of 6, giving it 2, 4, 6, 8. So it has the required octet. Now we've placed 2, 4, 6, 8, 10, 12, 14. Remember, each bond is 2 electrons. So we've placed all of our valence electrons. So this satisfies a correct dot structure. Let's look at our second molecule. Let's count up our valence. Carbon again has 4, and we have 3 carbons. Plus hydrogen has 1, and we have 8 hydrogens. So that gives us 12 plus 8 gives us 20 valence electrons. Let's put our 3 carbons here. Again, we know we can't bond everything to 1 carbon. That would violate an octet rule. So we place 2 4 electrons. Let's put a hydrogen here, here, and here. 3 hydrogens around the first carbon, giving it 2, 4, 6, 8. So that has the required octet. The second carbon, we don't want to put 3 hydrogens around it because it already has 2 bonds. So our middle carbon has 2, 4, 6, 8 electrons now. It has the required octet. And we have 3 hydrogens remaining, so let's put those around our last carbon, giving it the required octet. Now we've placed 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we placed 20 electrons, so we have no more. Everything has an octet. Our carbons do. Our hydrogens are all terminal. So here, this would represent a correct dot structure for C3H8.
So another thing about organic molecules, when we're writing their molecular formula, we can often write them in what is called a condensed formula. Organic molecules, as we said, can be sometimes fairly large, lots of central atoms, and their atoms can be bonded a lot of different ways. So the condensed formula gives us more information about how the atoms are bonded together. Let's look at the 2 molecules that we just drew the structures for, and here's their structures. We can see the chemical formula for the first one, C2H6, and for the second one, C3H8. Now there's really only one way the atoms can be bonded, but if we add more carbons, we can begin to bond them a little differently. The condensed formula for C2H6 would look like this, CH3CH3. That's because the dot structure, in the dot structure we have a carbon bonded to 3 hydrogens, so a CH3, and that carbon's bonded to a second carbon with 3 hydrogens, so CH3. So CH3CH3. Again, 2 carbons, 6 hydrogens. They're both correct, but this second condensed formula gives us a bit of a heads up about how the atoms are going to be bonded. Here with the second one, CH3CH8, we have 3 carbons, so 3 carbons, and 8 hydrogens, but we know that the first carbon is bonded to 3 hydrogens, so CH3. The second carbon is bonded to 2 hydrogens, so CH2. And then the third carbon is, of course, bonded to the carbon, but then 3 other hydrogens, so CH3. So the condensed formula, we often use that when we're examining organic molecules because, as I said, it gives us a bit more information. So become a little bit familiar with that. Now, organic molecules do not just contain carbons and hydrogens. They can also contain lots of other elements, not all the elements, but a select few of these nonmetals like nitrogen, oxygen, our halides, or halogens rather, phosphorus, sulfur. They can be also found in a lot of organic molecules. So for molecules that contain some of these other atoms like oxygens, nitrogens, our halogens, there's a few rules that we can kind of follow or keep in mind when we're drawing dot structures that will help us predict their structures correctly. So we've already looked at carbon a little bit, but there's a general rule for carbon. If you have a carbon in an organic molecule, it's always going to have 4 bonds, no lone pairs, and it's almost always going to be a central atom. So if you look at these 3 structures here, each carbon has 4 bonds. It may be a single and a triple or 4 singles, but in some form it has 4 bonds. All of the carbons are central atoms, so that's almost always true in organic molecules. If we have hydrogens, and this is true of any molecule that has hydrogens, but hydrogens are always going to be your terminal atoms. They're never going to be a central atom, and we'll never have lone pairs around a hydrogen, of course. Now, what if we have an oxygen in an organic molecule? Well, oxygens tend to have 2 bonds in some form and 2 lone pairs. So here you can see a couple of different examples where our oxygens have 2 bonds, either a double or 2 singles, and 2 lone pairs. Nitrogens are found in organic molecules. They tend to have 3 bonds and 1 lone pair. And we can also have halogens in our organic molecules, and they are almost always terminal atoms. And of course, they'll have 3 lone pairs in order to have an octet. So our halogens in organic molecules, we're talking about organic molecules only, they tend to be terminal atoms. Now, there's always exceptions to these, but these rules are true the vast majority of the time when we're dealing with organic molecule electron dot structures. So let's practice a few other organic molecules and practice drawing their electron dot structures. If you would, pause the video and see if you can draw these 3 electron dot structures correctly, and then we'll work them together.
So let's look at the electron dot structures for these 3 molecules. First, let's count up our valence. Let's do it for each one. So my carbon here, carbon has 4. We have 1 hydrogen. Each hydrogen has 1. We have 3 hydrogens, so that's 3. Oxygen has 6. Carbon is 4. And then again, we have 3 more hydrogens, so that gives us a total of 3. So that's 10, 16. So we have 20 total valence electrons for this first molecule. The second one, we have carbon has 4. We have hydrogen, 2 hydrogens, 1 each. And then my carbon has another 4. Hydrogen has 1. And then my chlorine has 7 valence. So if we add these up, we have 10, 18 total valence electrons. And then over here, my carbon is 4, hydrogen has 1, we have 3 hydrogens, nitrogen has 5, hydrogen has 1, carbon 4, and then my 3 hydrogens gives us an additional 3. So if we add this up, we have 10, 16, we have 20 valence electrons for this one as well. So Let's look at this first molecule. If you look at all three of them, you notice they're written in the condensed formula. So instead of C2H6O, we have CH3OCH3. So that gives me some information about how these are bonded. Now, I know that I've got a carbon here, and I know that my hydrogens must be terminal. Hydrogen can never be attached to two atoms. It can never be a central atom. So I have CH3, so we can write that like this. Now I have an oxygen. That tells me my oxygen is in between these two carbons. And then I have another carbon and 3 hydrogens attached to it. So based on the condensed formula, that gives me information about how these atoms should be bonded. Now let's count up how many valence electrons we've placed so far. We've got 2, 4, 6, 8. So this carbon has an octet, and we've had 8. So this would be 10, 12, 14, 16. So we've got 16, so we have 4 electrons remaining. Now, where do they go? Well, we can't put them around the carbons or hydrogens. That violates the rules. But we did say that oxygen typically has 2 bonds and 2 lone pairs. So oxygen has 2 4 electrons. To give it an octet, we want to give it those 2 lone pairs. Now we've placed the additional 4. We have 0 left. So this would be the correct dot structure for this molecule. Everything has an octet, except for hydrogen. Hydrogen is terminal, so that's good. Now over here, we've got CH2. So that tells me I've got a carbon with 2 hydrogens bonded to it. Now I've got another carbon with 1 hydrogen bonded to it. And then I've got a Cl. We know that our chlorines, our halogens, are generally terminal atoms. So let's count up how many electrons we've placed so far. We placed 2, 4, 6, 8, 10. So if I subtract 10 from this, I have 8 electrons remaining. So we have to put them in pairs around our terminal atom. So let's start with our halogen, because our halogen generally has 1 bond and 3 sets of lone pairs. So that's 2, 4, 6 electrons. So I have 2 remaining. Where do they go? Well, this carbon, I could put them over here on this carbon, or I could put them on this carbon. It doesn't really matter which one. I'm going to put them right here on this carbon, but if you put them over here, you'll see that's perfectly fine as well. So now I've put that lone pair there. That's 2, so that gives me 0 remaining. So now let's check and see if everything has an octet. This first carbon has 2, 4, 6. This first carbon does not have an octet. Our middle carbon has 2, 4, 6, 8. The middle carbon has an octet, and my chlorine has 2, 4, 6, 8. So everything has an octet except for the first carbon. Well, our last rule for drawing electron dot structures tell us if something doesn't have an octet, we can take a lone pair and make it into a bonding pair. So I'm going to take the lone pair on this carbon. It has to be on this carbon, not the chlorine. I'm going to erase it, and I'm going to convert it into a bonding pair between those 2 carbons. Now let's check. We've got 2, 4, 6, 8 on this carbon. That's good. 2, 4, 6, 8 on this carbon. And we still have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this would be a correct dot structure. Now if you did put the lone pair on this carbon, then your middle carbon would be short an octet, and you would take that lone pair and again put the double bond here. So you would end up at the same place whether you put the lone pair on the first or second carbon. Finally, let's take a look at this one. Okay. Now here we've got a CH3. Let me drop down a little bit. We've got a carbon, hydrogen, 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 CH3. We've got a nitrogen with a hydrogen, NH, so that tells me we've got an NH probably there. And then I've got CH3, CH, H, H. So let's count up how many electrons we've placed so far. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that gives me 2 electrons remaining. Where do they go? Well, they can't go on this carbon. Of course, they can't go on a hydrogen. They can't go on this carbon. But nitrogen generally wants 3 bonds and a lone pair. So if we put that on here, we can see that gives my nitrogen an octet. Now carbon, nitrogen, In this carbon, they all have octets. We've placed all 20 of our valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is a correct dot structure for our last molecule. So again, based on our condensed formulas, it gives us information about how the atoms should be bonded. So be sure you're familiar with drawing electron dot structures for organic molecules.